So following on from the previous video, we're trying to find out the number of terms needed to get this area to within this level of accuracy. Now, in order to work out the number of terms needed, we need to think about the remainder. But then, in order for us to make use of the remainder, we will need to show that the alternating series will actually converge. Once we have an alternating series that converges, then we can make use of the remainder. So you see what I mean later. So in the previous video, we got to this stage here. So when you integrate this, this thing here from 0 to 1, the whole thing here will equal this. So we now need to show that this thing here is an alternating series that will converge. Once we've shown that it's an alternating that converges, then we can make use of this thing here. We can make use of this. So next step is to show that this thing here is an alternating series that converges. So next step is to show that this thing here, this alternating series converges. So we need to check that all three will be satisfied. So the first step is to remove this alternating component, and then just concentrate on the UN. Well, make sure they're all positive. But while n is moving from 0 to infinity, n is always positive. Therefore, n factorial is positive. This thing is positive. Therefore, the whole thing is positive. We need to show that it's non-increasing. Well, as n increases, you can see the denominator is just going to get smaller and smaller and smaller. So, you can think of it as being like this: n plus 1 we've done this many times. So n plus 1 and then plus 1 again. This next term will always be bigger than this thing here. Therefore, it's going to get smaller and smaller. It's non-increasing. And then make sure that the limit heads towards 0. Well, make sure that the limit equals 0. So as n tends to infinity, the denominator is just going to get bigger and bigger. Therefore, the whole thing will head towards 0. So all three, we've done this many times. So I'm assuming you can accept all three have been satisfied. So here, this alternating series does indeed converge. And then now that we know that now that we have an alternating series that converge, we can make use of this thing here. If you have an alternating series that converge, then the remainder will be less than or equal to the value of this one term here. So all the remainders here, the remainder will be less than this thing here. Okay, so what that means is this thing here. What this means is we have an alternating series that converges. What it means is that the remainder will be less than the next term here. Well, the next term here will be you putting n plus 1 into here, and then putting n plus 1 into here. Okay, so the remainder will be this n plus 1 and then n plus 1. This capital hang on. Up here you've got small n. So n is moving about all the time. N is increasing. But then we know that there will be one number, capital N, where, well, this capital N represents a fixed number. Okay, so now tidy this up. That will then take you to here. So this is our remainder here. Now we want our remainder to be strictly less than 0.001. We want our remainder to be less than this, because right from the start of the previous video we said we want it to an accuracy of this or of this. So we want the remainder to be strictly less than this. So now it's just trying to work out capital N. So take the reciprocal. So that will then give you this. Because of this factorial thing here, we don't know how to solve this elegantly. So we're just going to guess. When capital N is 3, this whole thing here will be this. Well, we want this thing here. We want this whole thing here to be bigger than 1000. So when n equals 3, it gave us 216, which is no good. now guess again. Let's guess. We guess it to be a 4. When capital N is a 4, it gives us this whole thing here will be this, which is good because this thing here is bigger than this thing here. So capital N equals 4 is good. So what that means is capital 4. What that means, because it starts at 0 here, we need 5 terms. What it means is we need 5 terms. 1, 2, 3, 4, 5. Now add all these up. That will then give you this, and then this is our estimate here. But then our error, well, this is good enough. You see, this is our answer here with 5 terms. With 5 terms, it will give us this answer here. Well, looking at this could be an 8, or it could be a 6. So 8 or a 6. So if you work to 2 decimal places, this here would be a good enough answer. It would be, yeah, this here is a good enough. If you work to 2 decimal places, this here would be good enough. Okay.